Here we're going to look at how we obtain the mechanical energy balance from the steady state first law of thermo, essentially. And then under some conditions, how that reduces, simplifies to the Bernoulli equation. And the idea is that we use the mechanical energy balance often for processes where we don't have chemical reactions, we don't have a lot of heat transfer, things like flow through pipes, emptying out a tank through a spigot, if you like, and pumping liquid to a higher level in a pipe. So let's look at just a representation. First, I'll draw one possible way we might apply this. So imagine we have a fluid flowing through a pipe that is angled downward, so there's change in potential energy. We have a velocity at the inlet, different velocity at the outlet, and likewise a pressure at inlet and potentially a different pressure at the outlet. And the diameter of the pipe is larger at 0.1 than at 0.2. So let me write down the general energy balance, first law for a steady state system. And then let's look at how it simplifies. So here's the first law, and let's make all the terms clear. M dot, that's a mass flow rate. Delta H, change in enthalpy, the final. Enthalpy at 2 minus enthalpy at 1. And this just means that this is a specific enthalpy. So this would be joules per kilogram, for example. U is velocity. So this is the kinetic energy term in the first law. The gravitational constant, which is 9.81 meters per second squared in SI units. Z is from the diagram. This is the height difference, so it would be Z2 minus Z1. This is heat added per time, so the rate that heat is added. And this is the rate that work is done. So again, this is, if we add work, this is positive. If we add heat, Q is positive. So that's the first law, steady state. Now let's look at how we simplify it, apply it to develop the mechanical energy balance. So first I'm going to write down, so I'm going to divide through by M dot. So then on the left side, I'm going to replace delta H by its definition, delta U plus delta PV, where again this is specific volume. The delta U squared over 2 and G delta Z, they have the same form. But on the right side I have Q dot over M dot, and I have shaft work divided by M dot. So now we'll make some simplifications, and they're important parts of this mechanical energy balance. So we're going to assume incompressible. So the fluid, for example, if it's water, that's a good assumption. If it's a gas at relatively low velocities, it can be a good assumption. And what that means is, again, I'm going to rearrange in this second term. I can write it as specific volume times delta P, because I'm assuming that there's been no change. It's a constant term. Density hasn't changed. Specific volume hasn't changed. I can bring it outside. It's the same at 0.1 and 0.2. And then let me just rearrange the equation. So I've grouped these two terms together here, and this we're going to refer to as frictional loss. It's a term that's going to be greater than 0. Often this term's going to be small. There's not much temperature change. Delta U, small. We use the term F for that. Again, specific. And so this, then we use F with the hat indicating, per kilogram. And this term here we can write as delta P over density, since density is just 1 over specific volume. Well, that then is the mechanical energy balance, so I'll just rewrite it to make it clear. Well, let's suppose that friction losses are small, so this is approximately 0. Let's assume that there's no work, no shaft work. Then the equation simplifies to just the pressure drop over rho plus delta U squared over 2 plus G delta Z is equal to 0. Well, this is then the Bernoulli equation.